Okay, so for your day 3 notes, yesterday we talked all about a parallelogram and its properties, and applied them to some algebra questions. Now what we want to do is apply all those properties to our proofs. So quick reminder of our properties: opposite sides parallel, along with opposite sides being congruent, opposite angles congruent, consecutive, 2 in a row, consecutive angles supplementary, and finally diagonals bisect each other. So when we're starting to do these proofs today, we want to keep these 5 properties in mind because it may help us, say if we're trying to prove 2 triangles congruent, it may help us get a pair of sides or a pair of angles where maybe in the past we'd have to do addition, subtraction. That's not available anymore, and we're going to have to rely on one of these 5 properties. So I'm going to start you with a very basic proof, and then we're going to increase in difficulty to an honors level proof at the very end. So if we take a look at this first one here, both of these quadrilaterals are parallelograms. So again, all these 5 properties apply. And we're trying to get WX congruent to ZY. And we see there's no way this is going to be a 2-step proof because WX and ZY are in 2 separate parallelograms. So right off the bat, I'm going to start using a property here. And that is to say that, hey, WX, the one in the proof statement, is congruent to its opposite side, VT. And just like we wrote a couple times yesterday, parallelogram implies opposite sides congruent. We can write this next step in the same statement as number 2, but I'm going to separate it just so you guys see exactly what I'm about to do. I'm going to take ZY, the other segment in the proof statement, and take a look. ZY also has to be congruent to VT using the same reason. Again, I could have put both in the same statement because I have the same reason, but I just wanted to make sure you guys saw what was happening. So both WX and ZY are both congruent to VT. So a little thing in the past we called substitution says, hey, those 2 have to be congruent to each other. Okay, so not a very long proof, but again, take a look. We're starting to use our parallelogram properties in these proofs. So pretty basic one right there. Let's up the difficulty for the next one. Now actually let's prove some triangles congruent. You'll see in the givens here, we are told that ABCD is the parallelogram, and that's important. If you guys are using highlighters or colored pencils, make sure you know that ABCD is the one we're talking about here. Right? That is the only quadrilateral I can apply my parallelogram properties to. A lot of people look at this and think EBFD is the parallelogram because it looks like one, but nope. The only thing I can apply my parallelogram properties to is to ABCD. A couple other givens here. DF is congruent to EB. And that's really about it here, huh? That's really about it. Okay. So again, we're trying to prove the triangle's congruent. So I have 5 methods, as you guys remember: side, 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 angle, side, angle, side, angle, 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 side, and good old HL, which I don't think is going to be used here because I don't see any right triangles. All right, so right now in those 2 triangles, we do not have anything, no sides or angles. So, all right, we got to dig deep here and find some on our own. So let's start by using the properties of a parallelogram. We can say EA, sorry, wrong side. How about DA is congruent to CB because they are opposite sides of that parallelogram. So parallelogram implies opposite sides congruent. That gives us a pair of sides in those triangles. In the same step, I'm also going to go and say the other pair are congruent as well. DC and, DC and AB. Now, am I going to put an S next to that? Heck no, I'm not. All right, that's not part, those aren't sides in the triangles, but they are going to get me sides in the triangles. If DC and AB are congruent, using those two and the given pair there, that DF and EB, I can do a little subtraction and get another pair of sides. So I can say DF minus DC equals EB minus AB. Subtraction. And things don't change even though we're in Unit 6. It's going to be substitution coming up to say that side EA is congruent to side CF, and that is another pair of sides. All right, so I have two pairs of sides, so I need one more pair of something. And now look, we may struggle a little bit with this third pair, but at least narrow down the choices. We already said it's not going to be HL. Can't be angle, angle, side because I have two sides. Can't be angle, side, angle. Same reason, I already have two sides. So it's coming down to side, 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 and side, angle, side. So I either get the two remaining sides congruent to each other or the angle in between. And the way I'm going to do it here is I'm going to get the angle in between. All right, I'm going to get angle EAD congruent to FCB. Not because they're right angles. Again, they may look like them, but we have nothing that says they are. What we're going to do is we're going to go back to the properties of a parallelogram. And we're going to say the opposite angles are congruent. So angle DAB is congruent to angle DCB. Parallelogram implies opposite angles congruent. Now, what the heck am I going to do with that? Well, if they're congruent, so are the angles supplementary to them, right? Supplements of congruent angles are congruent. That's how I'm going to get the other pair of angles in those triangles equal. But before I do that, I can't use that theorem unless I tell you what angles are supplementary first. So angle DAE and angle DAB are supplementary, along with the other pair, angle BCD and angle FCB. Linear pairs are supplementary. And now I can say those supplements are equal. So angle EAD is congruent to angle FCB. Supplements of congruent angles are congruent. And there is the A I needed for side angle side. So step 8, finish it up. Tell me those triangles are congruent. And we're all set. Okay, so yeah, hey, take a look. Again, you usually know from doing these proofs that, hey, the first two come pretty easy. It's the third pair that are a pain. And again, that's how we found the third pair. We use the opposite angles are congruent to say the supplements are congruent. Won't be the last time we have to prove triangles congruent. Take a look at our next one. Go ahead, write all your givens in. Okay, the whole thing's a parallelogram. We got perpendicular lines, so I know I got right angles on both sides. Probably only need one, but not both. And now I'm looking for SE congruent to QF. So I take a look at SE and QF. They are not sides, so I can't say that they're congruent right away. As you guys have known from our Unit 4 and some of our indirect proofs, the only way we get segments congruent is prove triangles that contain those segments congruent. So we're going to have to prove triangles first, so we got to make a decision right now. SE and QF, we need to find two triangles that contain SE and QF, and I can only find one pair that have SE as a full side, and that's triangle SEP, and only one triangle that's got QF as a full side, and that's QFR. All right, and we have nothing right now, nothing as far as we can count as angles and sides. So let's take care of the two-step process for the right angles. First step is saying the right angles, so angle PES and angle QFR are right angles. Perpendicular lines form right angles, or if you guys write definition of perpendicular, whatever floats your boat. Now say they're congruent right after. And there's an A for us. There's an angle. Next up, I think the next easiest to look and see is, hey, because it's a parallelogram, side PS is congruent to its opposite side, QR. Parallelogram implies opposite sides congruent. So that gives me a pair of sides. And finally, now here's that darn third pair, right? That we have to search and search for. Hopefully going forward, after I give you this piece of advice, these angles or sides will be a lot easier to notice going forward. If you are given a parallelogram, and there is at least one diagonal drawn in, like SQ is drawn in, if there is one diagonal drawn in, you're going to have alternate interior angle somewhere, without a doubt. So if you have a parallelogram with at least one diagonal drawn in, you will have at least a pair of alternate interior angles. And there they are. Angle PSE and angle RQF are alternate interior. But we're not ready to say they're congruent. They are not congruent unless I know those lines are parallel. And how do I know they're parallel? Well, it's a parallelogram property. So PS, not only is it congruent to QR, it's also parallel to QR. Parallelogram implies opposite sides opposite sides parallel. Now I know what's going to happen is some of you aren't going to have the confidence to put down, you're going to be unsure of yourself which lines are you going to need parallel. Is it PS and QR, or is it the other pair, SR and PQ, right? You're going to be 50-50. Am I going to guess? Am I going to get it correct? Easy solution, put both down. Okay, put both down. If you're unsure if it's PS and QR versus PQ and SR, put both down. Remember, correct extra steps don't get credit off. All right, so if you're ever unsure what lines need to be parallel for those alternate interior angles, just put both down, guys. You can't go wrong. Now I can say the alternate interior angles are congruent. So angle PSE is congruent to RQF. Parallel lines, and this goes back to Unit 3. Ooh, parallel lines imply alternate interior angles congruent. And that gives me my third pair that I needed. Now I just got to figure out what the method is to say triangle PSE is congruent to triangle RQF. And some of you may already know, is that side in between or not? Take a look. Absolutely not. So we have to go angle, angle, side. And there's a reason we got the triangles congruent. So we could say all their corresponding parts are, including SE and QF. And let it roll off the tongue, everybody. CPCTC. All right. So again, anytime you have a parallelogram with at least one diagonal drawn in, start sniffing around for alternate interior angles because they will be there. Whew. All right, we're rolling right along. Last one. Oh, buckle up. Buckle up for this bad boy. You thought it was bad finding that third pair before? Oh, wait till this one. Wait till this one, kids. All right, everything's in there. Got a proof triangle. That doesn't seem bad, right? Proof triangles. We've been doing that all day today. All right, so let's get an easy pair, right? Let's get the two easy pair out of the way of sides and angles. I'm going to go angle A, congruent to angle C. Parallelogram implies opposite angles congruent. There's an A. And also, why not the sides while we're here, right? DA congruent to CB. Parallelogram implies opposite sides congruent. All right. And now the dreaded third pair, right? Where can I go from here? Well, take a look. Givens are provided for a reason to use them. And we have not used those yet. Now, be careful on how you use those. E is the midpoint of AB. All that is saying then is AE is congruent to EB. And that's a problem because EB is not in one of the triangles I need. And then if you look at the other given, F is the midpoint of DC. All that's telling me is DF is congruent to FC. I need AE to be equal to FC. Okay, and it's not going to happen from definition of a midpoint. It's not going to happen from definition of a midpoint here. Whew. All right, so how are we going to use this then? Well, I hate to break the news to you, but you're going to have to go dig real deep to a theorem we used in Unit 2. Yes, let me repeat myself. Unit 2. Yes, a midpoint breaks a segment up into two congruent segments, but it also breaks a whole line segment in half. Let me say that again. A midpoint breaks a line segment in half. In half. So yes, if you remember back from Unit 2, we're going to use what was called halves of equal quantities are equal. Okay? Because what we're doing is take a look. If E and F are their midpoints of A, B, and DC, everyone look on your diagram right now at A, B, and DC. What do we know about those two line segments, A, B, and DC? You're darn right, they're congruent. So I'm just going to stick that into step 3 here. AB congruent to DC. They're congruent. And I'm going to take half of them. So I'm going to take, let's start here, half of AB. And what am I going to call that? Well, I got two options. I could call it AE or I could call it EB. Well, I hate to break it to you, but there's only one of those two line segments I'm concerned about in this proof, and that's AE. So I'm going to take half of AB and call this new line segment AE. And I'm going to do the same thing to DC. I'm going to take half of it and look at your diagram. You can call it DF or you can call it FC, but we're only concerned with FC. And the reason's not halves of equal quantities. How do I know I can take half of AB and half of DC? Because I had their midpoints. Definition of a midpoint. Now, I'm taking half. Take a look, everyone. I'm taking half of two equal quantities, AB and DC. So if halves of two equal quantities, they are equal to each other. So AE congruent to FC, and this is where I'm going to put halves of equal quantities are equal. And there it is. There's my other side that I needed. And you guys can tell why the two triangles are congruent now. So triangle DEA congruent to triangle BFC, side, angle, side. All right, so be alert for that because I think I put one similar to it on the homework. All right, if you're given the midpoint of two segments that are equal, make sure you try to use halves of equal quantities to get the partial ones equal. All right, guys, go ahead, start the homework, get your Chromebook out. Make sure you're looking at the answer key to check your proofs as you go along.